Alrighty. I want to do one more of our Descartes rule of signs before we look at our next piece. So I've got our function up here, we've got our f of x, and I want us to see if we can figure out how many positive, negative, and imaginary or complex roots we're going to have. Let's take a look at this. So first things first, let's start with how many positive roots are we gonna have on this? How do we tell? How many sign changes do we have in this function right here? Just one. So how many positive roots are we going to have? Just one. I can't count down by an even number because I can't have a negative number of solutions, a negative number of roots. That doesn't exist. So we have to have one positive root. There's no other option. What do we do to figure out negative roots? Substitute in that opposite of x. So we're going to say f of minus x and I'm going to write the whole thing out here, substituting in my minus x into the x to the fourth by 7 opposite of x cubed minus 4 times the opposite of x squared minus the opposite of x, minus 7. Again, if you can and or want to simplify it as you write it, you do not have to write this step down, but for some people, this step's going to be really helpful. For some people, this step's going to be critical. So if you can do it in your head reliably and accurately, you don't have to write it down. Just make sure we're doing it right. Because when we simplify this, anything with an even degree, our sign doesn't change. So this is going to be go back to being exactly x to the fourth. But my 7 times the opposite of x cubed, that one's going to change signs. Because we have that odd degree, that forces our function to change signs. So this one goes to being a negative. Bless you. When we have our opposite of x squared, we know that guy's not going to change signs. Totally fine. So this term is going to stay exactly where it is. Because the opposite of x times the opposite of x is the same exact thing as positive x squared. So this is still going to be our 4x squared. Opposite of x times negative x, or negative 1 times the opposite of x. We got a plus x. And then our minus 7's just kind of chilling. So how many negative roots are we going to have? Let's say, because we start positive and we instantly switch negative. So there's one change. Then we switch to positive, so there's two changes. And then we switch back to negative, there's three changes. So we could have 3 negative roots. Absolutely true. Or we could have 1 negative root. So it always counts down by even numbers. We count our sign changes. So we have 3 sign changes, so it could be 3, or if I take away 2, it could be 1. Yes, sir. The last thing we're going to do on this one is we're going to make that little table looking thing, because we need to figure out about our imaginary or our complex roots. So work towards putting it into that table, see if we can figure out our imaginary or our complex roots.
What is the reasoning behind skipping every other one?
Because imaginary numbers always come in pairs. So if I had, for example, if I had 1 positive root and we said it was 2 negative roots, that would leave me with 1 loose root somewhere that I was needing to find, and imaginary roots cannot come in a single term. Imaginary roots always come in pairs. So if we have an imaginary root, it's got to be 0 or 2 or 4. It always, always, always comes in pairs. So I will never just have 1 imaginary root. It can't happen. So that's why it's always counting down by 2s, is because if I have 1 root that's not positive or negative, I have to have another one. Because imaginary roots always, always, always come in pairs. So if we're looking at our kind of list of options we could do, I'm going to put it up over here. So we could have some number of positive roots, we'll have some number of negative roots, some number of imaginary roots for our total. How many roots in total are we going to have here? 4. It's our degree. Our degree is going to tell us how many roots we should have. So we know, why should I change our signs? Colors. Just switching the colors here. We already know for sure we're going to have 1 positive root. That's the only option I have there. For my negative roots, I might have 3 of them. And if I have 3 negative roots, how many imaginary roots will I have to get to my total? 0. Because I already have my 4 roots. I have 1 positive root, 3 negative roots, and I can't go bigger than 4. It has to be 4. But if I have my 1 positive root, but instead of the 3, if I have 1 negative root, 1 positive root and 1 negative root, how many imaginary roots would I need to have? 2. We cannot have 1 in the imaginary column, or imaginary root. We cannot just get 1 imaginary root. That does not happen. By the way imaginary roots are formed, they happen when we take the square root of a negative number, which means we're going to have plus or minus 2i, 3i, whatever that is. So we always, always, always have imaginary roots in pairs. That's why we always count down by an even number. Okay. I know it's been a minute since we did a Descartes, simply because I didn't see you guys yesterday. So this shows us how many positive, how many negative, and how many complex or imaginary roots we have to get to our total of 4 roots. Okay? Questions on that one? Okie dokie, artichoke. I'm going to give us a new definition. Again, wordy. more wordy than we need to have. I'm a sure. I'm gonna say 4.3 is all about the writing of the equation and finding A, doing those positivity tables, and writing it in factored form, then multiplying out to standard form. Yeah. 4.3 is Descartes finding A and putting it in factored form and multiplying it out. So 4.4, we're going to start having more of these complex roots, meaning imaginary stuff. And just like we were saying when we were looking at Descartes, imaginary roots always, always, always come in pairs, every single time. Sometimes we are not just going to have the root of 3i or 4i. Sometimes you'll get like 2 plus 3i or 4 minus the square root of 26i. Like all kinds of different things. So if we have a complex number, meaning it's actually something like 2 plus 3i as a root, like we're told, we have a root at 2 plus 3i. The conjugate pair, meaning if I multiplied it, it would be a difference of squares so that we could get rid of all the i's. The conjugate pair will also be a root. So if I know 2 plus 3i is a root, so will 2 minus 3i. Because if I was to multiply these two pieces together, I would get a difference of squares, and all of the i's would cancel out. Imaginary numbers always come in pairs, so it'll be like plus or minus 3i, plus or minus 2i, plus or minus I square root of 7. Or it can be as a complex number, 2 plus 3i and 2 minus 3i. This is the way the instructions are worded in this section. It just sounds severely overcomplicated. Where it'll say express it as express the polynomial as a product of linear and quadratic polynomials. Just means write it in factored form with no i's. This whole thing means factored form with no i's that cannot be simplified further. So we don't want it fully in standard form, but we want it as factored as it can be without giving us imaginaries. So that's what this whole paragraph means. Is factored form, no i's, simplified as much as possible. It's just saying it's irreducible over the real numbers, meaning I can't make it any smaller. So it is a very, very wordy way of saying factored form, no i's. And we're going to do one of these today, and we'll practice more of them on Monday. But the first one we're going to do is actually right here at the bottom. We're going to look at a degree 4, and we're told it has zeros at 2, minus 1, and 3i. Which means we know for a fact, since we have 3i right here, they always come in pairs, so this is going to be positive or negative 3i. Every imaginary root comes in pairs. It will either be plus or minus the imaginary number or the conjugate pair of the complex number. So if we just have an imaginary root, 3i, plus or minus 3i, drop on. So writing it in factored form, we build it exactly the same way. We're going to have leading coefficient. They told us up here that our leading coefficient is 1, so we don't have to put an A. I started to, but I forgot. Our leading coefficient is 1. So we're going to, oh, yep, absolutely, sorry. X minus R for all of our roots. R is root. Oh, this funky R?
Yeah.
It means over the real numbers. I have genuinely no idea why it changed the font to look like that. It's supposed to be like a capital R with an extra line. Like that. That'll be how it looks in the book, is capital R with the extra line. It just means that I could not make them smaller. I could not reduce them further. Irreducible means I cannot simplify more. I can't factor. X minus R for every single factor. So X minus each of our roots, just like we've been doing before. So for our factored form here, just because we have like 2 minutes and I want to get through it, I'm going to have X minus our first root at 2. X minus the second root at minus 1 becomes X plus 1. And then I need to use both of these imaginary roots. We're going to have our X plus 3i and X minus 3i. Because imaginary roots always come in pairs. This degree 4 helps us remember that we need to do that because I need to make sure we get 1, 2, 3, 4 x's. To make this irreducible over the real numbers, I need to get rid of the i's. We're not getting rid of any other pieces. We're not going fully out to standard form. I'm just going to multiply my pieces that have i's together. Because if we multiply those two pieces together, we'll get our x squared plus 3ix minus 3ix minus 9i squared, right, just for that piece, which simplifies down because these two pieces cancel out. And we also know that I squared is -1. So this whole term is going to simplify down to be x squared plus 9. And that is not something that could be reduced. That's not something I could factor to be smaller. The only way that this gets smaller is if we solve and get imaginary roots. So this is irreducible because I can't reduce it. I cannot make it smaller or factor. So this would be our answer. It is in factored form using real number coefficients. Everything's real, nothing's imaginary, and we're ready to rock and roll. We will practice more with these next week. Because it's, we could only do that if it was a difference of squares. If it was x squared minus 9, yes, absolutely. But sum of squares doesn't factor unless it's imaginary. We will work more with these next week, I promise. Just something I wanted to start with.